Time travel isn't science fiction. It's happening to you right now. GPS satellites orbiting above your head are gaining 38 microseconds per day relative to clocks on Earth, and without constant corrections, your phone's map would be off by over 11 kilometers every single day. The physics that makes this possible reveals possibilities far stranger than anything Hollywood has ever imagined. But the evidence isn't limited to satellites. Back in 1971, physicists J.C. Hafele and Hafele-Keating conducted what might be the most elegant proof of time travel ever performed. They synchronized 4 cesium atomic clocks with a reference clock at the U.S. Naval Observatory, then literally bought airline tickets for the clocks. Each atomic timekeeper got its own seat on commercial flights around the world. One set of clocks flew eastward with Earth's rotation, the other westward against it. When they returned to Washington and compared the traveling clocks to the ones that stayed on the ground, the results were undeniable. The eastward flying clock had lost 59 nanoseconds relative to the ground clock, while the westward flying clock had gained 273 nanoseconds. These weren't measurement errors. They were proof that time itself had been stretched and compressed by motion. The clocks had literally aged at different rates. What gets me every time I think about this experiment is how mundane it was. The clocks occupied regular passenger seats, complete with their own tickets. Passengers probably walked past billion-dollar scientific instruments, proving the nature of time itself, completely unaware they were witnessing history. The flight attendants served peanuts while Einstein's most counterintuitive prediction played out in the overhead compartments. This wasn't some exotic laboratory condition. These were ordinary commercial flights at ordinary altitudes, traveling at speeds that seem fast to us but are glacially slow compared to the speed of light. Yet even at those pedestrian velocities, around 500 miles per hour, time dilation was measurable down to the nanosecond. The universe doesn't care about our human-scale intuitions. Physics operates by its own rules, and those rules bend time whether we notice or not. The implications cascade outward from that simple airline experiment. Every time you board a plane, your personal timeline shifts relative to people on the ground. Flight attendants who spend their careers at 35,000 feet age microseconds less than their ground-based counterparts over decades of flying. It's an effect so small that it's meaningless on human timescales, but it's real, it's measurable, and it's happening. But here's what makes the GPS correction even more remarkable. The satellites aren't just moving fast, they're also escaping Earth's gravitational well. Einstein's theory predicts that clocks in weaker gravitational fields run faster than those in stronger fields. At 12,550 miles above Earth's surface, GPS satellites experience significantly weaker gravity than we do down here, causing their clocks to tick faster by about 45 microseconds per day. Combined with the velocity effect that slows them down by 7 microseconds per day, the net result is that satellite time races ahead of Earth time by 38 microseconds daily. Without constant correction, this seemingly tiny discrepancy would compound catastrophically. Your morning commute would become a navigation nightmare within days, with GPS coordinates drifting miles from reality. What happens when you accelerate particles to nearly the speed of light isn't theoretical anymore, it's engineering. At CERN's particle accelerators, subatomic particles called muons provide the most direct proof that Einstein's predictions aren't just mathematical curiosities, but physical laws that govern reality at every scale. Muons have a natural lifetime of just 2.2 microseconds when at rest in laboratory conditions. That's barely enough time for light to travel 6 in 60 meters. Under normal circumstances, These particles should decay almost instantly, making them impossible to study for any meaningful duration. But when physicists accelerate muons to relativistic speeds, screaming around a circular track at 99.9% the speed of light, something extraordinary happens to their personal clocks. Time itself literally slows down for them. The results from CERN's muon storage ring were unambiguous. These hyperfast particles lived for over 64 microseconds, nearly 30 times longer than their stationary counterparts. The muons weren't somehow becoming more stable or resistant to decay. Space-time itself was stretching. From the muon's perspective, it lived its normal 2.2 microseconds and decayed exactly on schedule. But from our perspective, watching from the slow lane of reality, those 2.2 microseconds stretched into more than a minute. What makes this result so unsettling is its inevitability. Einstein's equations don't offer escape clauses or exceptions. The mathematics is absolute. Nothing can exceed the speed of light. So when you push an object faster and faster, time must slow down to preserve that cosmic speed limit. Today, this time dilation is routinely confirmed in particle accelerators, and it is obligatory for engineers to calculate it when designing any modern physics experiment. The implications cascade beyond laboratory experiments. This exact effect gives us the time needed to accelerate particles to extreme multi-TeV scales. It is the very foundation for next-generation particle colliders. Giant accelerators currently on drawing boards will collide particles over distances of many kilometers, and these mega-machines are possible at all only because of time dilation. Every time CERN fires up its accelerators, it's not just smashing particles together. It's demonstrating that time is not a universal constant. The universe operates on principles so counterintuitive that particles routinely experience time at rates that would be impossible under our common-sense understanding of reality. It's happening right now in machines built by human hands, proving that the strangest predictions of relativity are the actual operating instructions for the cosmos. After seeing muons live 30 times longer than they should at near-light speed, do you think time dilation could ever be noticeable in human lifespans if we built fast enough spacecraft? Drop your answer in the comments below. But particle accelerators aren't the only place where Einstein's predictions get extreme. Gravitational time dilation isn't happening in particle accelerators or on airplanes. It's happening right under your feet. The lower the gravitational potential, the closer you are to the source of gravitation, the slower time passes. Your head is literally aging faster than your feet. The difference is infinitesimal. We're talking about nanoseconds over a human lifetime. But it's real and measurable. In 2018, physicists at the National Institute for Standards and Technology proved this by comparing two atomic clocks separated by just 1 centimeter. At a precision of about 1 part in 10 raised 18 dollars, they detected the tiny difference in the frequencies of two clocks when one was just 1 centimeter higher in elevation than the other. The lower clock ticked slower than the upper clock by a measurable amount. 1 centimeter, about the width of your fingernail, was enough to detect gravitational time dilation. But in 2022, researchers at Gila pushed this to an almost absurd extreme. They measured time dilation at the smallest scale ever, showing that two tiny atomic clocks separated by just a millimeter tick at different rates. The experiments demonstrate that the distance between the tip of a pencil and where you grip it is enough for time to run at different speeds. This isn't just an abstract trick. These atomic clocks are now so sensitive to time dilation that they are used as advanced geospatial tools, capable of detecting tectonic plate shifts, volcanic magma movement, and changes in Earth's gravitational field just by measuring how fast time passes at different elevations. What makes gravitational time dilation so unsettling is how it scales. The effects we've measured on Earth are microscopic, but the mathematics suggest no upper limit. Relative to Earth's age in billions of years, Earth's core is in effect 5 years younger than its surface. The center of our planet has experienced 2.5 fewer years of time than the surface simply because it sits deeper in Earth's gravitational well. Now imagine what happens near a black hole. As an object approaches the event horizon, the passage of time for that object slows dramatically relative to a distant observer. An astronaut hovering near a black hole's event horizon would age more slowly than an astronaut orbiting safely far away. If the hovering astronaut remained near the black hole for what felt like 1 hour to them, several years might pass on Earth. This isn't science fiction speculation. It's the same physics that governs your GPS signal, just pushed to its logical extreme. Near a black hole's event horizon, time dilation approaches infinity. From the perspective of someone watching from a safe distance, a falling astronaut would appear to slow down and freeze just before crossing the event horizon, their image redshifted until it faded from view. But here's the truly mind-bending part. From the falling astronaut's perspective, nothing unusual happens. As you fall into a black hole, you don't notice any time dilation in your own frame. For you, time ticks at the exact same rate it always has. You would simply fall towards the black hole, pass the event horizon, and hit the singularity in what feels like mere moments. Two different observers, experiencing the same event, measuring completely different durations of time. The universe doesn't just bend space, it fractures our most basic assumption about the nature of time itself. If you had the chance to spend 1 hour orbiting near a black hole, knowing you would return to an Earth 100 years in the future, would you take the trip? Let me know in the comments. Right now, astronauts on the International Space Station are aging roughly 0.007 seconds less for every 6 months in space compared to someone on Earth. Scott Kelly, who spent nearly a year orbiting Earth, returned 5 milliseconds younger than his twin brother Mark, who remained on the ground. These are measured effects happening to human beings traveling at what we consider ordinary spaceflight velocities. The ISS travels at about 28,000 kilometers per hour, orbiting at roughly 400 kilometers altitude. That's fast by our standards, but it's less than 0.003% of light speed. Yet even at these pedestrian relativistic velocities, time itself bends measurably around the astronaut's journey. The mathematics of time dilation reveal possibilities that stretch far beyond low Earth orbit. For a 1% difference in aging, you'd need to travel at about 14% of light speed, roughly 4,500 times faster than the International Space Station. At 50% the speed of light, time would pass about 15% slower for the traveler. For dramatic effects like aging years slower than people on Earth, you'd need to exceed 90% of light speed. At 90% light speed, the mathematics become staggering. A 1-year journey for the traveler would correspond to roughly 2.3 years passing on Earth. Push that to 99% light speed, and 1 year of ship time stretches to 7 years of Earth time. At the extreme end, 1 year of travel might correspond to 10 years on Earth. These are engineering specifications for a universe that operates by relativistic rules. The implications cascade outward. A crew might volunteer for a 10-year mission, knowing they'll return to an Earth 50 or 100 years in the future. They're not just explorers. They're involuntary time travelers, launched into a future they'll never be able to return from. Every relativistic journey becomes a one-way trip through time, even if the spatial voyage brings you home. Forward time travel isn't a question of if. It's a question of when we build the engines fast enough to make it dramatic. Backward time travel confronts paradoxes that make forward time travel look simple by comparison. The most famous is the grandfather paradox. Travel back in time and prevent your grandfather from having children, which erases your own existence, which means you never existed to travel back in the first place. This creates an insurmountable logical contradiction. Stephen Hawking proposed the chronology protection conjecture, suggesting that unknown physical laws prevent such travel. In a 1992 paper, Hawking uses the metaphor of a chronology protection agency as a personification of the aspects of physics that make time travel impossible at macroscopic scales, thus preventing temporal paradoxes. He wrote, "It seems that there is a chronology protection agency which prevents the appearance of closed time-like curves and so makes the universe safe for historians." The mathematics behind this protection mechanism is surprisingly elegant. Hawking suggested that vacuum fluctuations near a closed time-like curve would become so intense that they would either destroy the time machine or create a situation where it could never have been formed in the first place. Quantum field theory intervenes to protect chronology. Attempting to form these closed loops threads the space-time structure with vacuum fluctuations, leading to a diverging energy flux that collapses the wormhole. Particles and antiparticles from the quantum vacuum separate, piling up until the entire structure destroys itself. Even the theoretical pathways to backward time travel require materials that may not exist. Construction of a traversable wormhole would require a substance with negative energy density, often called exotic matter. The wormhole spacetime requires an energy distribution that violates various foundational energy conditions. Negative energy density has been indirectly observed in minor quantum effects, such as the Casimir effect, but never in the amounts or scale needed to maintain a traversable wormhole. The universe seems designed to protect its own timeline from corruption. The same quantum mechanics that enables time dilation also appears to prevent paradoxes. The same relativity that allows forward time travel seems to forbid backward journeys that would unravel causality itself. It's as if the universe operates by a fundamental principle. You can visit the future, but the past is right protected. Recent research suggests that if backward time travel were somehow possible, any memory collected along a closed loop would be erased before the loop completes, the universe erasing its own evidence. Forward time travel isn't just possible, it's inevitable, happening to every GPS satellite, every high-speed particle, and every astronaut orbiting Earth. But backward time travel faces barriers so fundamental that they appear woven into the fabric of space-time itself. The universe allows you to leap into tomorrow, but yesterday remains forever locked behind the chronology protection agency of physics itself. Time travel is real. You're doing it right now, just very slowly. Subscribe for more mind-bending physics that's actually happening.